Look at this split-screen stock chart. Up top, we have a raw, day-by-day feed of a volatile market, erratic spikes, sudden dips, and constant false signals. But on the bottom, the noise is stripped away, isolating the structural, long-term upward trend. If you try to identify that bottom line using a basic day-to-day check, the code will fail. A simple linear scan resets its progress the moment it hits a minor temporary dip, losing the larger trajectory entirely. The longest increasing subsequence, or LIS, algorithm solves this by acting as a nonlinear low-pass filter. Instead of demanding every number be higher than the very last one, it skips over the transient downward fluctuations to find the underlying path of growth. Mastering LIS allows you to program a system to ignore noise and expose the structural path hidden within chaotic data. We will deconstruct this algorithm using a controlled sample of 5 stock prices: 10, 22, 9, 33, and 50. To store our results, we set up a dynamic programming table directly beneath our data. Each slot in this memory bank will track the length of the longest possible trend ending exactly at that specific price. We populate every slot in the table with the number 1 as our absolute baseline. In this mathematical framework, a single isolated number constitutes an increasing sequence of length 1. By establishing this baseline, we transform the problem into a systematic, documented audit of all previous states. Moving to the number 9, the algorithm performs a backward glance. It audits the historical prices to see if the 9 can extend an existing trend. Because 9 is lower than both 22 and 10, it cannot extend either of those trends. Its DP value remains at the baseline of 1. When we advance to 33, the audit succeeds. The algorithm identifies that 9, 22, and 10 are all lower prices that 33 can extend. Under the core DP role, when a valid extension is found, the algorithm inherits the past DP value, adds 1 to it, and updates the current state. Since 33 extends the chain of 10 and 22, it takes their DP value of 2, adds 1, and becomes 3. Let's test the logic. We move to the final number, 50. Pause the video here and calculate the final DP value using these inheritance rules. 50 is greater than every previous number. It checks their DP values, finds the longest chain ending at 33 with a value of 3, and increments that value to 4. This nested inner loop acts as a systematic historical audit, ensuring every update is built upon the most optimal past decision. We can translate this visual logic directly into a C++ nested loop. This line initializes the DP vector to the size of our input array, ensuring every slot starts with the mandatory baseline of 1. The algorithm uses a max function during the backward glance. If a number finds a valid, shorter sequence after already discovering a longer one, the max function prevents the smaller value from overwriting our best result. Walking through the array and glancing backward for every element results in a time complexity of O of n squared. While this is the foundational approach, you can optimize further. By incorporating binary search and patience sorting, the algorithm can reach a complexity of O of n log n. This 4-step workflow, initializing to ones, looking back, extending valid chains, and tracking the max, replaces complex recursion with a structured table of documented decisions.